Okay, so this could be theta too, like it says in the book, but I wrote x just because my thetas look really messy. We need to evaluate this integral, which means we need to know what the antiderivative of this term is. But to make it easier, the integral is a linear operator, which just means you can factor out that 2 and multiply it after you find the antiderivative and plug in those limits of integration. So the 2 can wait outside. And now this part, if you're not sure what to do, if it's a trig function, you want to look at a table of derivatives. Okay? The derivative of sine is cosine. Okay, you want to look at that table. So if you go further down in that table, the derivative of tangent is secant squared. So we want the antiderivative. We want something so that the derivative turns into secant squared. So that is tangent, because the derivative of tangent would make secant squared. So we got tangent x. We evaluate that between 0 and pi over 3. Okay, and so you plug in your limits of integration. So tangent pi over 3 subtracted by tangent 0. And so let's draw our triangles. Pi over 3 is the angle for tangent. So pi over 3, that's a 60-degree angle, if that helps. And a 60-degree triangle has the square root of 3 over 2 as one of the sides, and 1/2 as the other side. The square root of 3 over 2 is always opposite of the 60-degree angle. Okay. So tangent is the opposite of that reference angle divided by the adjacent of that reference angle. So square root of 3 over 2 divided by 1/2, that makes square root of 3. And then tangent of 0, the best way of doing that is using the fact that tangent is sine over cosine. And so cosine is the x-coordinate, sine is the y-coordinate. So you got 0 divided by 1 on the unit circle, so that makes 0. So I've got 2 square roots of 3 for a final answer of this integral.